Welcome to Maths with AJD. This is our second video on linear programming. And here we'll be considering key terminology in linear programming that will help us understand the the kind of things we talk about in linear programming. And straight to the point, the first thing we talk about in linear programming is objective function. Objective function. Okay. The objective function in linear programming, because linear programming is LP for short, the objective function in linear programming is a mathematical expression that defines the goal of the optimization problem. That is our target, Typically, it represents what we want to maximize, or minimize, such as profit. Of course, you want to maximize profit as much as possible. You want to minimize cost of production as much as possible, or you want to maximize the time you spend doing something. Okay. For example, a factory may a factory, for example, a factory may aim to maximize profits by producing a combination of goods within budget limits. So there are limitations, but then you still want to get the best of the situation. So if X is the number of products, if X is the number of product A and Y is the number of product B, so a possible objective function might be profit equals 50 times X plus 40 times Y. Okay, 50 times X plus 40 times Y. So you'll be wondering where the 50 and 40 are coming from, where coefficients 50 and 40 represent the profit, per unit of each product. Okay. So that's about objective function. So let's move on to the next idea, which is constraints. So you have the objective function, that's the actual thing you want to do, but then there are constraints, right? There are limitations. So constraints are the limitations. They are the limitations or restrictions imposed on the problem. Often based on resource availability, production capacities, or specific requirements. For instance, you have capacity to make 1,000 cements per day, but then you don't have enough limestone to do that. You see, that's a limitation. So you have to deal with that. Okay. So each constraint is represented by a linear inequality. The objective function, we saw that as, an expression like what we have here. It's an equality for the most part, basically, in fact. So each constraint is represented by a linear inequality. Very important to note the idea of inequality. Okay. So for instance, if our factory can produce up to 200 units due to material limitations. Okay, like the case of raw material I talked about the other time. Though we can do more than 200, but we are limited to 200 because we can't get all the raw material we need. So due to material limitations, the constraint, the constraint might, the constraint might look like this. Constraint might look like x plus y less than or equal to 200. So that's the constraint that if you add up all the materials you can ever get, it doesn't go beyond 200. So that's the reality here. So um, these inequalities, these inequalities define the boundaries, define the boundaries within which the solution must lie. So, I mean, in real life, right, there are always, there are always, constraints. There are always limitations for sure. They are bound to exist. Okay. Um, okay. So that's talking about constraints now. I think I want to talk about the types of constraints. That's really important. Types of constraints. And of course, other terms are coming up. Types of constraints. I think that's really important to talk about. Yeah. So in linear programming and optimization, constraints are critical components that define and shape the problem, just like we've said already, right? So let's talk about the following. Let's talk about the following types of constraints. Okay. Number one, we have equality constraints. We have equality constraint, just like the one we saw up there. So we can have equality constraints. So here, these constraints require a strict equality, a strict equality between so this constraint require a strict equality between expressions often written as, say, ax plus by equals c. So this is why it is called equality constraint. So this is exactly why it is called equality constraint. So this constraint requires strict equality between expressions often written as what you have here now. Okay. Then we also have inequality constraint, like the one we saw earlier, inequality constraints. Inequality constraints. So these constraints, restrict a value to either a minimum or maximum threshold. That a minimum or maximum threshold. So this can be less than or equal to, less than or equal to, which is less than or equal to like this, or greater than or equal to. Greater than or equal to, that's something like this. So less than or equal to or greater than or equal to constraints. Okay. Uh, such as limiting production to a maximum of 200 units. Okay. Of course, for equality constraint, right? Okay, we already saw equality there. I think that settles it. Then we also have so there are equality, inequality constraints. Then there are also bound constraints. Three, you have bound constraints. So these actually specify upper or lower bounds, on a variable. Like limiting x to values between 0 and 100. So in this way, we have something like 0 is less than or equal to x is less than or equal to 100. Okay. So which keeps solutions within realistic or allowable ranges. Realistic or allowable ranges. Then we can have integer constraints. maybe one day soon we'll get to integer programming. But for now, our focus is on linear programming. So we can have integer constraints. Integer constraints. Say, I mean, these are used in integer programming. Yeah, I mean, these are used in integer programming, which we are not really focusing on right now, but I mean, just mention that used in integer programming, they require certain variables to take integer values, only, often used in cases where partial units, e.g., half a product or half a human for that matter, half a product aren't feasible. Okay. So these are types of constraints, equality, inequality, and so on and so forth. Now, let's go on to another terminology in linear programming. So after constraints, we can talk about feasible region. Feasible region. Feasible region. So the feasible region, feasible region is the set of all possible solutions that satisfy all constraints of the linear programming problem. So in a graphical representation, it is typically the area on the coordinate, the area on the coordinate, on the coordinate plane where all constraints overlap, where all constraints overlap. So this region contains every possible combination, every possible combination of decision variables that meet the restrictions. So only points within this region are are viable for optimizing the objective function. Okay. Now, I think I like to do an example. Let's just look at this. So imagine that you have x plus 2y. X plus 2y is less than or equal to, say, 10, whereas you have x minus y is x minus y is greater than 5. So if you want to find a feasible region for this, right, usually the way to go is, you can say if you take x plus 2y less than or equal to 10, right, to find a feasible region for this, okay, I mean, you have to turn them to, okay, to find a feasible region for these two now. So you have to do something like this. X plus 2y is equal to 10. Remove the inequality sign. You're still going to come back to it. So you now say that at x equals 0, what that means is that you have 2y equals 10, which implies that y is equal to 5 if you divide, if you divide both sides by 2. So that means y is 5. So it means that you have 0, 5. So for x plus y equals 10 now, then now say at x equals, at y equals 0. So you're going to, if you set each variable to 0, you can get where it will intersect. So at y equals 0, it means you simply have x to be equal to 10. So it means you have 0, 5 and 10, 0. Here this is x, y. Then this is x, y. So y is 0, x is 10. So those 2 points are really important. So you have to, keep them. Or better still, yeah, let's keep them because we are going to need them later. Then you go to x minus y is greater than 5. So x minus y, um, okay. So for x minus y greater than 5, you do the same. So x minus y is equal to 5. So forget about the greater than. We are going to deal with that very soon. So x minus y greater than 5. So again, you say at x equals 0, what happens? You have minus y equals 5. That simply implies that y is equal to minus 5. So it means you have 0 minus 5. Okay, you keep that. Then you now say that at y equals 0, x is simply equal to 5. So you have 5, 0. Okay, so again, keep these two. So see what is going to happen. So you come, okay, the most positive y, the biggest y is 10. I mean, the biggest y is 5 rather, and the smallest y is minus 5. So, and then the biggest x is 10. Okay. So, I mean, let's just do something like this. So you can now come and have something like this. This is your x. This is your y. So this is, let's say this is 2, 4, 6, 8, 10. I think we have x that is up to 10. And the biggest y is 5, while the least is minus 5. So you have that. And this is like minus 2, minus 4, minus 6, and so on. Then for y now, maybe you now have 1, 2, 3, 4, and 5. And then you have minus 1, minus 2, minus 3, minus 4, and minus 5. Okay. So we are interested in looking for the feasible region. So for the first one, right? When x is 0, y is 5. Okay. When x is 0, so x is 0 along the y-axis. When x is 0, y is 5. That is this point 0, 5 now. So this is point 0, 5 up here. Then the other one, when x, I mean, when y is 0, x is 10. So when y is 0 along the x-axis, so this is this. So this is 10, 0. Okay. So you can now join the points together. Missing that point now. So you join that together. Now, but you see, it's saying, so if you cannot go back to the original thing, the original thing says that x plus 2y is less than or equal to 10. Less than or equal to 10. So less than or equal to 10 is definitely going to be the other side. This is 10 now. If you shade the right-hand side of the line, it means you're talking about greater than 10, but the region we need is less than or equal to 10. So you shade this reverse direction this way. So all this area is less than or equal to 10. Okay. That's for the first one. Okay, let me try to extend this a bit. Okay, in case we need more. All right. Then so you can go to this line now, this line is actually so that line is x plus 2y equals 10. So this line is x plus 2y equals 10. Then we go for the second one, x minus y equals 5 now. So we have when x is 0, y is minus 5. So this is when x is 0, y is minus 5. So this is 0, minus 5. Okay. Then the other one, when y is 0, x is when y is 0, x is 5, that's when x is 0, y is 5. Or no, when y is 0, rather, x is 5. When y is 0, x is 5. So that means x is 5 around here. So this is 5, comma 0. Okay. So again, you can join the lines together, join those 2 points together like that. So now, then what are we looking for? We need x minus y greater than 5. So this is 5 here. So if you shade the right-hand side, see, if you shade, or should I say down? If you shade the downward part of the graph, okay. All right. Um, okay. So if you shade the downward part, we are looking at x minus y is greater than 5, right? So if you shade the downward part, this is 5 right here. This is 5 here. So if you shade it down, it means you are going greater than 5. So it means you have to shade the other direction. Okay. Oh, sorry. X minus 5 is greater than 5. Sorry, greater than 5. Sorry. Greater than 5 means you're going to shade down because this is 5. So if you shade down, it covers 6. So you see, this is 5 right here. So you're going to shade this direction. So you're going to shade this direction. Okay. Now, the feasible region is basically where the blue lines intersect the green lines. So it means that if you're going to shade out trace out the feasible region, now it will be something like all this area. Okay. The feasible region is where the blue lines meet with the green lines. Okay. This is the feasible region. So you see the feasible region where the blue lines meet the green lines. That's a feasible region now. So, I mean, it looks like an endless region, but if we had like x minus y less than 5, so we'd have shaded up here. So it means that the feasible region can be somewhere in this area, but from what we have, this is it. So we're going to do more of this as we go on later. So that talks about feasible region. Okay, the region that satisfies all the imposed conditions. That is what you call the feasible region. So let's talk about the next thing we want to talk about. So we've talked about objective function constraints. We've seen types of constraints, and then now we want to talk about decision variables. Decision variables. Um, decision variables. Decision variables. That's like types of decision variables. This types of decision decision variables in linear programming. In linear programming. Okay. Okay. Types of variables. All right. So let's talk about decision variables. Yeah. Decision variables. Okay. Decision variables. Okay, yeah. Decision variables represent represent the quantities. They represent the quantities we control, or adjust to achieve the optimal solution. So these are the decision variables to achieve the optimal solution. Okay. So in our example, um, X and Y could be decision variables where X is the number of units of product A, like we said before, and Y is the number of units of product B. Okay, so these variables form the foundation. They form the foundation of the mathematical model as their values determine the outcome. So the values of these variables determine the outcome of the objective function. Okay. Now, there are different types of variables in linear programming, right? And it's important to really to consider them. So in linear programming, decision variables can be classified as restricted. So the variables can be restricted and unrestricted, based on the limitations placed on their values. Okay. So let's talk about restricted variables. Okay. These variables have specific bounds or limitations on their values. They can be constrained. To be non-negative. Can be non-negative. I mean, typically represented as, say, X is greater than or equal to 0. So here we are imposing a non-negativity condition on the decision variable. So they can be constrained to be non-negative, or they might be bounded. They might be bounded within a certain range. Such as 0 is less than or equal to X is less than or equal to 10. I mean, it's less than or equal to 100 or whatever you choose. Okay. So restricted variables are commonly used. They are commonly used in situations where only non-negative quantities. Non-negative quantities make sense. Okay. There are situations where if you have a negative value, it doesn't make any sense, such as production level. So you can't say you produced minus 10 products, such as production levels, resource allocations, resource allocations, or even human populations, right? Resource allocations or time spent. Time spent cannot be negative. Okay. Where negative values will not be realistic. Where negative values would not be realistic. Okay. Then we also have unrestricted variables. We have unrestricted variables. As the name implies, right? No boundary, no condition imposed on them. So these variables, sometimes called unrestricted in sign, unrestricted in sign, can take any real value, including 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 positive, negative, or zero. Positive, negative, or zero. So they are typically used when there's no limitation on the direction of the variable's effect. Okay, of the variable's effect, such as financial gains or losses in a portfolio. Temperature fluctuations, or changes in inventory levels. Changes in inventory levels that could either increase or decrease. Okay, so those are unrestricted variables. So I also like to see mathematical notation for unrestricted variables. Unrestricted variables. Okay. Uh, mathematical. Okay. Yeah. So, so if you have an unrestricted variable x, right? If you have unrestricted variable x, given an unrestricted variable, given an unrestricted variable x, the unrestricted variable can be expressed as the difference between its positive part and negative part. So we can express it as x equals x plus minus x minus. So whenever you have whenever you know that a particular variable x is unrestricted, so you can express that unrestricted variable as the difference between the positive part and the negative part. So x is x plus and minus x minus. So here now, that simply means that the x plus part is greater than or equal to 0. That's the non-negative part of x, and the x negative part is the non-positive part of x, often considered as a debt or negative quantity. So the non-positive part of x, which is less than 0, okay? That should be less than 0, like that. If you have a variable that can take on both positive and negative values, it can be written as this amount by which it's positive and negative. Yeah, so basically that's the idea here. So with that, we are done with decision variables. Let's see if we have another term called optimal solution. That's the solution you get at the end of the day after doing all the iterations you need to do. So we have optimal solution. Optimal solution. That's the last idea, the last terminology. Optimal solution. Optimal solution. So the optimal solution is the best possible outcome. Is the best possible outcome based on the objective function. Based on the objective function within the within the constraints within the constraints of the feasible region. So it represents the maximum or minimum value of the objective function. Okay. So in many LP problems, in many linear programming problems, the optimal solution, the optimal solution, the optimal solution is found at a vertex. It is found at a vertex or corner point, vertex or corner point of the feasible region. Okay, of the feasible region. I mean, what that means is that we did an example. Okay, so probably um you can imagine that probably the optimal solution can be somewhere around here. We are not sure. I mean, because you're not solving a real optimization problem. I just came up with that. So the optimal solution could be somewhere around here. Probably if you had a third line, say you had another line, which is something like this, and then the feasible region is now here. So maybe this vertex or this vertex, you can find the solution around it. But I mean, as we go on, we'll be taking real examples so you will understand better what we mean by that. Okay, so So you can, so in many linear programming problems, the optimal solution is found at a vertex or corner point of the feasible region. Okay. So for our factory example, solving the linear programming model will give specific, values for X and Y that maximize profit, that maximize profit constrained by material availability. Constrained by material availability. So these are basically the terms you have for a linear programming problem. So using these terms, a linear programming problem is set up to find values for the decision variable that lead to the optimal solution. Okay, I mean, let's take that again slowly. So a linear programming problem is set up to find values for the decision variables x and y, for instance, that lead to the optimal solution of the objective function while respecting the feasible region defined by the constraints. Okay, so at the end of the day, right, you're looking for, so in summary, if I may do that, in summary, in summary, LP problems, LP problems are LP problems are about looking looking for the looking for the decision variables, looking for the decision variables, say X, Y, or whatever you want, looking for there are specific decision variables, right, that lead to the optimal solution. So, we've talked about decision variables that lead to optimal solution, okay, of the objective function. So it means there are many solutions, but then there's only one optimal solution, or there can be a few optimal solutions that lead to the optimal solution of the objective function while while respecting while respecting while respecting the feasible region, while respecting the feasible region defined by the constraints, defined by the constraints. So you can see this is a summary of linear programming. So again, in summary, LP problems are about looking for decision variables that lead to optimal solution of the optimal solution of the objective function. So already should be objective function. Objective function. So we're looking for the optimal solution of the objective function while respecting the feasible region defined by the constraints. Okay. So those are the terminology we have talked about today. So objective function, constraints, feasible region, decision variables, optimal solution, and that's it. So thank you for following up to this point. If you have not subscribed to this channel, you can already see that you have a lot to learn here. So be sure to do that right away and hit the notification bell so you can get alerted each time a new video is released. Then don't forget to comment. Tell me if you want me to teach a particular a topic or you want me to solve a problem. Then after that, don't forget to like and also share so that more people can have access to this great learning. So expect the next video, which will be on how to formulate a linear programming problem. Till then, keep enjoying maths. Bye.